Hello, my name is Harry Crocker, and I will be presenting my Physics Lab 4 on circuits. The purpose of this lab was to predict and measure the behavior of circuits and examine resistors and capacitors. In this presentation, I will be going through the introduction, conservation in series circuits, RC circuits, and finally a discussion. Some of the fundamental principles that will be applied in this lab is Kirchhoff's loop rule, which is where the sum of all the voltages in the circuit add up to zero, the node rule, which is that the sum of the current entering a node equals the sum of the current leaving, and Ohm's law, which is voltage equals current times resistance. So to start off with actually doing the lab for the prediction and procedure, um, I predicted that I1 and I2 would be 0.02 amps. Total resistance is 147 ohms, and then I equals V divided by R, which is 3 divided by 147, which is equal to 0.0204. And then simulating the circuit, which is shown in the picture on the right, the measured I on the ammeter 1 and 2 was 0.2 amps, and then reversing the connection, the readout of the ammeter stays the same. So for part two, replacing the ammeter with a voltmeter. So the voltage is 3 volts and the current is 0. And then you can see on that table there's the potential difference between all those different points using Kirchhoff's loop rule and summing all the voltages to 0. It proves this rule in this part. This graph here shows the a potential difference between varying points in the circuit as measured, shown in the table earlier. And you can see that once it hits the 47 ohm resistor, the voltage difference drops to 0 because there's no voltage through, or no potential difference between the resistor because current stops flowing. So why doesn't the ammeter reading change after attaching the voltmeter? And that is because voltmeters have infinite resistance. Reading off the ammeter after connecting the voltmeter across the 100 ohm resistor, the current was 0.02 amps, and replacing the voltmeter with an ammeter in parallel, I1 and I2 were both 0.06 amps. Ammeters have 0 ohms, so current does not travel through the 100 ohm resistor. And then on the right there, you can see the resistance calculations using Ohm's law by dividing the voltage by the current flowing through. For the RC circuits portion of the lab, the circuit was set up with a 9-volt battery, a 200 microfarad capacitor, and 30 ohm light bulb. The voltage was measured and the capacitor was discharged, and then a plot of 20 seconds of voltage versus time data was collected. So here is the experimental data. You can see the time and voltage outputs over the 20-second period, and then that was plotted. That was linearized by taking the natural log of the voltage divided by initial v naught, and then you can see there on the right there's that linearized graph. These equations also represent some of the relationships that are shown here. Here are my calculations. You can see there the natural log was taken, and these were pulled directly from the data that was shown on the previous slide. We know the slope from the graph is equal to this value, so negative 1 over RC can be said equal to that slope. To solve, which was found to be 5.88, in reality it should be 6, which means that there was a 2% error in this experiment. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So in reality, ammeters actually have a tiny bit of resistance, which would have resulted in a voltage drop across the ammeter, and the current readouts would have been impacted because of that. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So in an ideal case where there's no resistance, the capacitor would charge instantly, but in reality, the battery is going to have some internal resistance, and so will the wires connecting the battery to the capacitor, so it won't be as instant.